In today's lecture, we will discuss applied optimization. So, whatever we have done so far with different derivative techniques and also in the previous lecture, we have been discussing about higher order derivative test. We have discussed about maxima and minima. So, we'll be using all those ideas to optimize certain problems. So, this is where the fun lies. We'll begin with a very simple numerical to help you understand the power of optimization. So let's first understand the question. We need to find two numbers whose sum is 24 and the product is as large as possible. So this is what we have to work with. So we'll start with two numbers. Let x and y be the two numbers such that, so we'll use the first condition here. Their sum is 24. Let this be equation number 1. And we need to find the product. The product must be as large as possible. If we denote our product with P, so this will be x times y. So we have to choose the number x and y in such a way that the product is always going to be the largest product possible. Okay, so how to do this problem? Here, the hint here is that we need to maximize the product. So this is where we will start our problem. Now P is a product of x and y. Clearly there are two variables. So we can say that our product P is a function of two variables x and y. But in order to perform the optimization, we have to convert it to a single variable. That's very simple. What we'll do is take equation number 1 and isolate y from here. So this will be 24 minus x. So let's substitute this value back into a product. So we have product is equals to x multiplied to 24 minus x. So this is equals to 24x minus x squared. So now we have a product which is entirely a function of x alone. Now we'll try to maximize this particular product. To do that, all we have to do is find its derivative with respect to the independent variable x. This is going to give us 24 minus 2x, and we set this value to 0. This is going to help us find out the value of x. The value of x will be 12. So here 12 is the critical value. So that means for this particular value of x, it could either maximize the product or it could also minimize the product. We do not know for sure whether if this is the maximum value or not. For that, what we need to do is perform the second derivative test. All we have to do is take dp over dx and again find its derivative with respect to x. So this will be equals to negative 2. So that means at x equals to 12, this is our value. So when we consider x equals to 12, then d square p over dx squared calculated at x equals to 12. So this is, since this is a constant, this will be simply negative 2, and negative 2 means it's less than 0. And recall from our second derivative test, when the second derivative gives us a negative value, we say that x equals to 12 will become the maximum value. So this is the point of maxima. So now that we have the value of x, the value of y will be equals to 24 minus 12. So y is also equals to 12. So that means we have two values, both of them are 12, such that their sum is going to be equals to 24 and the product is going to be as large as possible. For instance, let's say we can have different possibilities of x and y. Let's say x has the value 10, then y must have the value 14. Now when we multiply x times y, so that gives us 140. And if we have x equals to 12 and y equals to 12, then the product is 12 times 12 will be 144. So we can take any combination of x and y. For any combination of x and y, this is the only value, 12 and 12, which gives us the maximum value of the product will be 144. All other values of the product is always going to be lesser than 144. You can check. I'll give you one more example. Let's say we take x to be very close to 12. Let's take as 11.99 and y is equals to 12.01. So the product is 143.9999. Still it is lesser than 144. So that means we have optimized our problem in such a way that the value of x and y only when it's 12, then we are going to get a maximum product. Fine. Let's do another problem. So here it says that amongst all the rectangles inscribed in the circle, the square is going to have the maximum area. That means that we have a circle of certain radius, then different types of rectangles can be inscribed within the circle. So we have a rectangle. Let's say this area is A1. We'll consider another rectangle whose area is A2. And we'll consider a third type of rectangle, which is actually a square. A square is also a rectangle because it follows the criterion of being a rectangle. That means the opposite sides are parallel and equal. So this is area A3. So it says that whatever rectangle we take, it's only the square which is going to have the maximum amount of area. So let's try to optimize this problem. So we will have to find out the area. So let's consider a circle having a center O, and within the circle we have inscribed a rectangle A, B, C, D. Now we'll have to use a little bit of geometry here. We will drop a perpendicular from the center O to the base of this rectangle. Let's call it M. And we join the vertex A with the center, and this will become the radius of the circle. We'll call it R. We'll also consider that the length of the rectangle be 2x and the width be 2y. Then we can immediately say here that the value of AM, so this will be x, and the value of OM will be y. Now, in the right triangle OMA, which is right angle at M, we can use the Pythagoras theorem to say that r squared is equals to x squared plus y squared. So we'll consider this as equation number 1. Fine. And what about the area of this entire rectangle? So our area of the rectangle, here we only consider the area of the rectangle. We do not have to worry about the area of the circle, because in the problem we have to optimize the area of the rectangle. So the area, let it be represented by A. So this is clearly 2x, the length, multiplied to the width, which is 2y. So this will be 4 times x, y. Now, our area, which we have to optimize here, now this is a function of two variables, x and y. We have to omit one of the variable and convert it to a function of single variable. For that, we can use equation number 1. All we have to do is replace the value of y and write it in terms of x. So that means our area, which will be now a function of x, that can be given by 4x times. So instead of y, we will have square root of r squared minus x squared. So this is our area function. Let's call it equation number 2. What we have to do is we have to maximize this particular area function or optimize it. For that, we will take its derivative with respect to x. Now, I'm pretty sure that by now you are very much comfortable with obtaining the derivative. So what I will do here, I will write the result. You can perform the calculation. That this will give us 4 times r squared minus 2x squared whole divided by square root of r squared minus x squared. So this is going to be the derivative of area with respect to x. In order to optimize it, we will have to set derivative of a with respect to x equals to 0. And in doing so, we get the value of x, which will be equals to r divided by square root of 2. All you have to do is simply set this particular expression on the right hand side to 0, and solving for x, you should get r over square root of 2. So we will box it for the time being and label it as equation number 3. So this is actually a critical point. So we do not know for sure if it is actually maximizing the area or it is minimizing the area. For that, we will perform the second derivative test, which will tell us for sure that this is indeed going to maximize our area function. For that, we again have to take this equation, which is the first derivative of our area function, and again we have to take its derivative with respect to x. So let's do that. So we have the second derivative of a with respect to x. Again, you can perform the derivative by using the quotient rule. And again, I'm going to go ahead and write down the result. So this will be 4 times negative 4x divided by square root of r squared minus x squared minus x multiplied to r squared minus 2x squared whole divided by r squared minus x squared raised to the power of 3 over 2. So this is going to be the second derivative of our area function with respect to x. Now we will calculate this second derivative of our area function calculated at x equals to r over square root of 2. All we have to do is plug the value of x into this particular expression, and this is going to give us a value which is negative 16. Since negative 16 is less than 0, so we can say that x equals to r over square root of 2 is the maxima. This is the maxima value. Now we go back to our original equation, which is y is equals to square root of r squared minus x squared. This will help us find out the value of y, the width. So if we substitute x with r over square root of 2, this is also going to give us r over square root of 2. Clearly that the value of x is equals to value of y, and when the length is equal to the width, we say that our rectangle is the square, and this area of this particular square is, since it is maximum, so our initial statement, which we say that amongst all the rectangles inscribed in a circle, it's the square that is going to have the maximum area. Let us do another problem. Problem number 3. So this is a very interesting problem. Let's read out the problem first. We have a square piece of cardboard with side 24 inches, and this is to be made into a box by cutting out equal sizes from the corners and then folding up the sides to produce an open top box. What should be the side of the square that needs to be cut off so that the volume of the box is maximum, and also find out the maximum volume of the box. So let us begin. So we have a square cardboard, and the length of this cardboard is 24 inches. What we have to do, we have to cut off equal sizes from each of the corners. So let's say we have squares cut out from each of the corners of this cardboard piece. Once that has been cut off, we will fold it along those dotted lines, and this is going to give us a box. We need to find out the volume of the box, the maximum volume of the box, and also what size of this particular piece of particular square piece that has been cut out. We need to find its dimension as well. So let us begin. So we will consider that the small squares that have been cut off from each of the corners has a length of x. So each of them has a length of x. Now because it has a length of x, so we are remain with a size 24. We have to subtract x from both sides, so that will be 24 minus 2x. Similarly, this length is also going to be equals to 24 minus 2x. Now that we have all the dimensions, let us try to find out the volume of the box. So the volume of the rectangular box, which is denoted by V, so that will be equals to, we have 24 minus 2x. So since the base is a square base, so this is simply squared multiplied to the height. So our height will be the length x. So this is the volume of a rectangular box. We can also simplify this. We can multiply this expression to get 4x cubed minus 96x squared plus 576x. So let's consider this as equation number 1. So this is the volume of the box, and the box does not have any top. It's an open top box. All we have to do now is to maximize this volume. Since this is only a function of x, so we need to find its derivative with respect to x and equate it to 0. So let's begin. So dv over dx, so that's equals to derivative of 4x cubed, so this will be 12x squared minus 96x squared, so this will be 192x plus derivative of 576x, so this is 576 we set this equals to 0. So this is a very simple quadratic equation. All we have to do is use the quadratic formula and solve for x. So x is going to give us two values. X is going to be equals to 4 and x is going to be equals to 12. Now, we cannot consider the value of x to be equals to 12. So this is not possible. Can you think of it why? Now see, here we have considered that the length of the box is 24 minus 2x. So if we have x equals to 12, then this will simply goes to 0, which is not possible. So we are discarding the value x equals to 12. We have only one value, x is equals to 4. Now, this x equals to 4, we are not sure about it. So it could either maximize the volume or it could also minimize the volume. So to be entirely sure, all we have to do is find the second derivative. So we'll use this to find the second derivative. So let's do that. So we have d squared v over dx squared equals to, so second derivative of the derivative of 12x squared, so that's 24x, minus derivative of 192x, so that will be 192. And let's substitute the value of x with 4. So this gives us 24 times 4. So this will be 96 minus 192, which gives us negative 96. Now this is a negative number less than 0. So indeed, this is the maxima. So since this is maxima, now that we have the value of x, so we can say that the square that was cut off from the cardboard edges has a length of 4 inch. So 4 inch was cut off from, a square of 4 inch length was cut off from each of the edges. Now that we have the value of the edge, we can also find out the volume. So we'll substitute the value of x equals to 4 into this equation. So let's do that as well. So our volume will be 4, which is x times 24 minus 2 times 4 squared. So this is 4 times 24 minus 8. That will be 16. So we have 16 squared, and this gives us a value 1024 inch or cubic inch. So this is the maximum volume of a box. Problem number 4. What is the minimum amount of material required to construct a cylinder of volume V? So this is a problem of minimization. So let's say we have a cylinder whose volume is V. And we'll consider that the radius of the cylinder is R and it has a height of H. Now these are our assumptions, R and H. R is the radius, H is the height. What is the volume of the cylinder? The volume of a cylinder is given by pi times R squared H. Let this be equation number 1. Here we have been asked to find a minimum amount of material which is required to construct a cylinder. So minimum amount of material means we need to find the radius and H that should be as small as possible in order to have a minimum volume possible. Fine. So for this, we will have to minimize the area. So let's consider the surface area of the cylinder. So surface area of a cylinder is given by pi r squared plus 2 pi r h. So this is the surface area of a given cylinder. Now our surface has two parameters, the radius as well as the height. So what we'll try to do, we will remove this h by using the formula from equation number 1, because v here is a constant, it is fixed. So from here, we can find that our h value will be equals to v over pi r squared. So we'll substitute this value into this equation. So our surface area now becomes pi r squared plus 2 pi r. Then instead of h, we have v over pi r squared. So a few of the terms will get cancelled out. So pi and pi gets away, and r goes away, leaving us with s equals to pi r squared plus 2v over r. So now we can see that the surface area of the cylinder is entirely a function of the radius r. So let's this be equation number 3 and the height be equation number 2. Here I've missed a value 2. The surface area is 2 pi r squared. So this is 2 and this is 2 as well. Okay, now we'll try to minimize this surface. For that, all we have to do is take the derivative of the surface area with respect to radius, and we'll set that equals to 0. But first, let's take the derivative. So we have 2 pi times derivative of r squared will be 2r. plus 2v. We have 1 over r, so its derivative will be minus 1 over r squared. So let's set this equals to 0 in order to minimize it. So this will be 4 pi r minus 2v over r squared, which is equals to 0, where 4 pi r is equals to 2v over r squared. R cube will be equals to v over 2 pi. Solving for r, we have cube root of v over 2 pi. So this is the value of r, but this is only going to be a critical point. We exactly do not know for sure if it is going to minimize or maximize the area. So we'll again take the second derivative of s. So this will give us, we have second derivative of s with respect to r squared. So this is the first derivative, so let's take its derivative with respect to r. So we have 4 pi minus 2v, we have 1 over r squared, and that will be negative 2 over r cubed. So this is 4 pi plus 4v over r cubed. Now the radius is always a positive value, and 4 pi is positive, so that means this entire value is going to be greater than 0. We don't have to care about the value, only have to check the sign if it is positive or negative, since it is greater than 0. So this is now the minima value. Now since this is minima value, so we have obtained a value of r, which is going to minimize the volume. Now that we have r, we can also find out the value of h. So we consider h to be equals to v over pi r squared. H is equals to v over pi r squared. Substitute the value of r. This gives us v over pi times r is v over 2 pi whole raised to the power of 2/3. So this is the value of the height. If we do some simplification, we should get v over pi whole raised to the power of 1/3 times 2 raised to the power of 2/3. So this is the value of h and r. These are the dimensions that we need to choose in order to get the in order to obtain the cylinder with minimum value possible. Problem number 5. So this is our final problem. Here we have to find a point on the curve y equals to 1 over x, and this point has to be such that it is closest to the origin. So let us begin. First we'll look at the graph of y equals to 1 over x. What we have to do is find a point on this graph such that this is closest to the origin. So let's call this point P. So this is x comma y. So y here is 1 over x. Similarly, if we consider the point P equals to negative x, since we are in the third quadrant, this will be negative 1 over x. We'll have to find this particular point which is closest to the origin. Let's join the origin and the point P and denote this distance with d. Using the distance formula, then the value of d will be simply equals to x squared plus 1 over x squared. So this is the distance. Now what we'll do, we'll try to optimize this distance. We know optimize means we need to minimize this distance. So we have to take its derivative with respect to x. So let us do that. So derivative of d with respect to x will be equals to, so this derivative will be 1 over 2 times square root of x squared plus 1 over x squared times derivative with respect to x of x squared plus 1 over x squared, which is equals to 1 over 2 times square root of x squared plus 1 over x squared multiplied to derivative of x squared is 2x, and derivative of 1 over x squared is negative 2 over x cubed. We set this equals to 0, and since this is always a positive quantity, all we have to do is 2x minus set this value equals to 0. So this will be equals to x raised to the power of 4 is equals to 1. That means x is going to have the value plus or minus 1. I'm going to have 4 values, 2 of them are 1 and 2 of them are negative 1. So we have x equals to plus or minus 1. So that means the value of d, this is going to be whether we choose a positive value or negative value, doesn't matter. We are squaring it. So we'll take plus or minus both. 1 divided by plus or minus 1 whole squared. So that means we are saying that we are getting the value of d equals to square root of 2. But we are not exactly sure if this value is actually the minimum value or not, this distance. So what we'll do, we'll also check the endpoints as well. So let's do that. So we have d given by square root of x squared plus 1 over x squared. So in the limiting case, when x approaches infinity, then x squared plus 1 over x squared, so this blows to infinity. So we have positive infinity, so this goes to positive infinity. And in the limiting case, when x approaches negative infinity, infinity from the left hand side, so we have x squared plus 1 over x squared, so this goes to infinity. And the limiting value of the function, when x approaches 0, the distance d goes to infinity. So at the endpoint, we observe that the distance is extremely large value. So only possibility is that d is equals to square root of 2, and this is going to be the minimum value, the minimum distance from the origin to the point on the curve, square root of 2. So this is how we can use the method of optimization to find out the optimal cases as per our required needs. See you in the next class.